On the right corner, weighing 170 pounds, the Lord of Calculus, Sir Isaac Newton. On the left corner, weighing 80 kilos, because he was German. The machine from Berlin, not really Switzerland. Albert Einstein.
Hold on.
Brought to you by the Extreme Gravity Institute.
Thank you for adding that. But we can understand Newton's laws of motion. I mean, it's really basic stuff that we can witness right here on Earth.
Yes.
Every object in a state of motion tends to stay in motion unless acted on by an external force.
Yeah.
Because of that, we also understand mass, the relationship of an object's mass and an acceleration and applied force.
Yeah.
All these basic theorems or ideas of science.
Yeah.
And I forget what the third law of motion is. For every action, there's an equal and opposite reaction.
That one's important.
Yes, but those are the three laws of motion, basically.
Yep.
But through all of this, it works very well on Earth. With a little time, even a fourth grader today could understand Newton's laws of motion.
Yeah.
How long is it going to take before E equals mc squared could be explained to a fourth grader?
Oh, you're killing me. E equal mc squared. That's not the most important equation that Einstein constructed. Come on,
What's
Chris.
the most popular one?
It is unfortunately the most popular one. I blame the bomb,
Right.
but whatever. I honestly don't think that I think the basics of both special and general relativity, Einstein's theory, can be taught in high school. There's absolutely nothing that prevents you from doing that. You cannot really teach in high school differential geometry and topology and all of the mathematical intricacies that, go into the theory that you really need to understand if you're going to be doing research on that. But, if you're doing, if you are an astrophysicist and you're trying to model the motion of the planets in the solar system, because maybe there's a 10th planet, maybe there isn't, maybe there is, maybe there isn't, then you don't need just those three laws. You need quite a little bit more of mathematics. And you need to know how to create computer code that can solve those equations. And we don't teach that in high school, yet we teach the laws. So there's always a reduction that you can make from the main theory that can easily be explained in high school. And in fact, we are one of the things we work on at the Extreme Gravity Institute is this idea of trying to construct lesson plans for high school and middle school students where we can bring down the material that Einstein developed at a language that's both interesting, accessible, and serves a particular, learning purpose for middle school students. And, it's very difficult. That's why you work with lots of, educational specialists, but yeah.
But at the time when Newton discovered and wrote down his laws of motion, that was groundbreaking. Nobody was thinking that way. And eventually now, as I said, a fourth grader with a little time and a little study can understand it and get through it. Do you believe there will be sometime in the development of humans that because Einstein's theory of general and special relativity have been around, that it's just so ingrained in society that we'll be able to do it even at a very young, early age?
Yeah, I think we're moving toward that. We're going toward a transition of understanding how to explain this at a level that is more accessible to everyone. So absolutely, I think it started maybe 10, 15 years ago, and it will continue for the next 20, 30 years. In 20, 30 years, I think it'll become fairly standard. The problem is that we're trying to pack so much material into what students learn in middle school and in high school that it's difficult. If you add more, then either you make the day longer, which is not possible, you make the school day longer, I guess that's possible, or you remove some other material from the curriculum, and that's not feasible because the curriculum is very carefully crafted.
Right.
But you know what? You mentioned something interesting. You said, well, Newton wrote this, blah, blah, blah. Actually, Newton didn't write down things until Halley, like the guy from the comet.
Yes.
Was like, I think you should write this down. And Newton was like, I don't know. People don't like me. The writing is tough. And then I have to publish it. Like, no. You should write it down. And specifically for Kepler's problem. And he also didn't have a lot of money to publish back then. You had to have... You had to be well endowed.
You needed a patron.
You needed a patron. And the royal, astronomers sort of did not like him because they were a bit arrogant. I mean, this kid was 24. And when he like solved motion in the solar system, he was 26. He also invented, optics, or discovered some of the basic laws of optics. And by the way, when he was sort of solving the Kepler problem, the motion of the planets around, that's what Halley did. He came to his house and he was like, hey, nobody really understands why objects black holes, planets are moving in ellipses. And Newton's like, well, let me think about it. I'll get back to you. And a few months later, comes back to Halley and says, like, oh, here, like, I figure it out. It's like, oh, how did you do that? Well, I had to invent this new math, calculus, in the process. But, it worked out. Ta-da, now we have Kepler ellipses. And he was 26. It's sort of crazy, right?
Right.
I mean, granted that Leibniz in Germany was also at the same time developing and inventing calculus, but there's no way that they knew about each other. And today, we like to say Newton invented calculus because we adopted the British guy's conventions and notation, but we might as well also say that Leibniz invented it. But regardless, it's pretty astonishing. And Einstein, he was also 26, roughly 26, in his young 20s, early 20s.
Before I ask the follow-up to that, you want to take a phone call?
Sure, that's it.
It's 406-522-TALK. Caller, thanks for hanging in there. You're on the air. What's your question for physicist Nico Yunes?
I guess the question I got, and obviously I've enjoyed some of your conversations, but how does what you are doing relate to the prevalent theory of evolution? It seems to me that this stuff is hard to imagine that all of this knowledge, all of this ability crawled out of a little bottle of slop somewhere somehow, and yet we have all of these mighty outer space things and all the things you are just barely learning are out there. The two don't seem like they would coincide.
Yeah, excellent.
Thank you for the question, sir.
Excellent question. So really the theory of relativity and Newton's theory of gravitation have absolutely nothing to do with the theory of evolution of Darwin. Nothing pretty much at all. So what Newton and Einstein are trying to do, they're trying to describe phenomena that they observe happens with celestial bodies, or if you're talking about gravitation. I mean, for Newton, you're also talking about optics and other things like that are more earthbound. But where evolution and physics begin to intersect has more to do with the theory of the Big Bang that maybe at some point we will get to.
Yeah, well, that's very interesting that you bring that up, because I've made the comment before that you can mathematically trace back everything to just the millisecond after the Big Bang, but not the actual moment itself.
Yeah, so the idea is that the universe, one model is that the universe started with at a point of infinite pressure and infinite density and infinite awesomeness, and it all exploded violently and expanded, creating the galaxies and the stars that we see today over a period of like 13 billion years or something like that. And somewhere in between there, maybe a few million years ago, I'm not an archaeologist, so do not quote me on this, or a biologist for that matter, life began to develop on Earth, and, according to the theory of evolution, it sort of started in a swamp, and then, at a microscopic level, life began to develop, and then larger forms of life developed from that, and then, sea life began from that, and then that sea life moved out of the oceans into land, and then monkeys, and then other,
so
life, and so on, and then Newton.
So we're all stardust.
Yeah, but that's different. That's different because, if you think about it, we have iron in our blood. It's sort of important to have iron in your blood. Not only because steak is awesome, but I'm Argentinian, so I have to say that, right? We love our beef. But also because the only way you can make iron in the universe is in the center of stars. Like when stars burn, some of their byproduct is iron. And the only way for that iron to get to us is for these stars that had iron to explode.
A supernova.
A supernova! And for some of that iron to then get to Earth and mix with everything else that was mixing in this giant primordial soup to then, form life. And so all of the ingredients of life, if you want, sort of originated if you trace it sufficiently back, to stars. So, Sagan was right when he was saying that we are stardust.
We started this conversation as Newton versus Einstein.
Yeah.
And
who was cooler? Is that what you're going to ask me?
well, yeah, who was cooler?
I don't know. I mean, I'm sort of biased, right? My entire scientific life has been about studying Einstein and his theory. But Newton was like the big daddy. He was the one that was like, and here's calculus and optics and gravitation, and by the way, the laws of motion. Come on, who does that? By the age 26? Wow. But Einstein was like, he was a rock star.
Right.
He was the man. And, I am a little bit biased, and so I would side with Einstein.
Well, then, not being the coolest, but with the incredible achievements that Einstein brought to us, and the incredible achievements, as you just delineated with Newton, is the process the same?
Yeah, it's interesting. So we know a lot about Einstein's process, mostly because he was much more recent than Newton, and we kept records much better. Right. Also because he was a bit of a rock star, and so people interviewed him and were asking these questions to him. Newton was different. Newton wasn't very politically savvy. Sort of people did not like Newton very much, especially academics. He could come off as a bit arrogant and know-it-all, and he sort of did know it all, so he had a reason to act like that. But still, he did not play well with people typically. So we don't know, I in particular don't know much about Newton's scientific process, and I don't know how much we actually know of that. What we do know is that Einstein really thought about science and nature through thought experiments. Why thought experiments? These are experiments that happen in your head, in your mind. You imagine, what would it be like if, for example, I was standing on a train platform and a train went by and somebody inside the train turned a flashlight on. What would you see? What would the person in the train see? What would the person in the platform see? Or what would happen if you try to, ride on a train, because they didn't have spaceships back then, faster and faster and faster and faster until the train approaches the speed of light. So these are experiments. Obviously you can't do this speed of light experiment in real life. There's no train that can travel that fast, ever. But you can imagine what would happen. And that's called a thought experiment, or a Gedanken experiment, if you want to go German. And I imagine that at some level, Newton also must have had to think about science in that way. What happens if, I throw whatever the equivalent of a baseball was in the...
A pomegranate.
An apple. I hear he liked apples.
Yes.
Why is it that the apple falls? Or what happens if I throw an apple at an angle, or more importantly, if I shoot a cannon or a trebuchet at my enemies? At what angle do I need to, point my cannon so that I can hit the wall of my enemy's castle? And these are things he could imagine, and things he could go and sort of experiment on. He could build lenses and study optics. That's the kind of basic science that he invented and developed. Not the creation of the lens, but sort of understanding how light behaves as it propagates through optical media. Einstein couldn't do that. Einstein didn't have a spaceship. He didn't have a black hole he could go to and it's yeah, very interesting, So the processes had to be different because one had experimental access and the other one didn't. I mean, they were both theorists, but Newton could go and throw an apple up in the air, whereas Newton could not jump on a train that was traveling at the speed of light.
So, do your thought experiments in your work today, are they still applicable?
Yeah, absolutely.
Oh.
So we think about these things all the time, especially when we're trying to push the boundaries of knowledge. So, for example, I was just telling you about these gravitational waves we detected and how they came from these two black holes that formed this one very massive black hole, 70 solar masses. And we don't know, how is it that we started with two 30 solar mass black holes? How do you create a binary system? That's what it's called. So two objects moving around each other with that mass. So we start thinking and creating, thought experiments. Well, what would happen if, for example, you had one star that was just spinning very, very, very fast, and as it collapses into a black hole, it sort of breaks into two lumps because of the rotation, and then it forms two black holes, and now you're in a binary system. Like, that's a thought experiment. You can't just go and make a star spin that fast and break into two black holes. Like, we don't have the ability to do that, and we don't have the ability to go and observe what's happening either, because it's too far away and too dim to actually look at telescopes or look through telescopes at events like that. So we have to think about it and say, with everything we know about physics, okay, electricity, magnetism, optics, gravity, we throw all of human knowledge to this problem. Can this thought experiment happen? And what would the outcome be? And then you write a paper. Then people complain about it.
You do the math, and you have another group of students saying, that's wrong, because of blah, blah, blah.
Exactly.
Do you have any final thoughts before we wrap things up regarding Newton versus Einstein?
I think it's fascinating to talk about Newton and Einstein and to debate, like, who was right. They were both right, it turns out. Who was cooler? They were both really cool. But in some sense, we are comparing apples and oranges. Obviously, Newton would be the apple here. I think they were both great. You're talking about geniuses of humanity. And as such, I think we should celebrate them both equally.
Well, Nico Jones, as always, I appreciate your time. Thank you for it this week, and I look forward to our next conversation next week.
Yeah, absolutely. Thank you, Chris.